Good morning, everybody. Welcome to our last seminar for this term. And today we have Dr. Laia Comas Bru from Reading University. And Yuval, go ahead and present our speaker.
Thank you. Well, I'm very happy and privileged to introduce Laia. We've been working for a while together. Laia studied marine sciences in Vigo, right? And she also holds a master's in coastal geosciences engineering from Kiel. Then she started her PhD with Professor Frank McDermott, who some of you may know, in paleoclimate. That's in the University College Dublin. There well, I'll sum it up in one sentence. She researched everything with oxygen isotopes, from rainfall to soil, water to karst, then to speleothems. And now she's working she's a postdoctoral research assistant doing paleohydrological data analysis at the University of Reading with Professor Sandy Harrison. Which brings us to a more recent project, and actually the reason why we invited her today, and that's leading the first phase of the Pages-sponsored working group, SISOL, which is Speleothem, Isotope Synthesis and Analysis. Within the context of SISOL, she pursued primarily climate model evaluations using the SISOL database, and she did that as a Charlemagne Scholar of the Royal Irish Academy, sorry. And for that work and her work with SISOL, Laia was awarded the World Climate Research Program and Global Climate Observing System International Data Prize, that's a long name for a prize, 2020, for outstanding contribution in data generation, management, and preservation. So, did I get everything right?
Yes, you did. Thank you very much, Yuval. And thank you for inviting me today. It's a pleasure to be here online with you all. So what I'm going to be talking about today is about my experience in SISOL, what we've done, what we've achieved, and why that's important, and a little bit like the next steps that SISOL is going to be taking over. So I'll talk about several different things. I hope, yeah, you don't get lost and you find this exciting as I find it. So basically, Yuval has already introduced SISOL, and for those of you who don't know what this working group is, it is a Pages-sponsored working group. And Pages working groups are like temporary organizations that bring paleoscientists together to target things that would not be able to achieve individually. So it's like a platform that puts community people together to do like big questions. So basically what we proposed back in 2016, end of 2016, was to put together all the speleothem data that was available there and create a global database. At the beginning, the first motivation for that came from my current supervisor, Sandy Harrison, who's working with benchmarking and paleoclimate model evaluation. And the idea was to bring speleothems on the table because they weren't standardized or within a single framework, a database framework. So people in that community weren't using them. So basically, these were, like what you have on the screen, are the first objectives that we set up for the first phase. Each working group in Pages has phases, 3-year phases, and these were our objectives for that first 3-year phase. So basically, we started like, why speleothems? Are there enough? Aren't there? Like, there was no evaluation as to how many speleothems were there published globally. Everybody knows some records, some are very famous, some others are not being, that they don't have that big name. So we started putting together, and that started like 2011, 2012, together with Yuval and some other colleagues as, okay, what's out there? And this is what we put together, like a map of all the records that have been published since the early 90s. And you can see on the top right that publications increased since the mid-90s quite exponentially. So there were plenty of records, and most of them were not available on the repositories such as that of NOAA. So this is not updated, but more or less it gives you an idea that the records available in NOAA were around 200. We identified around 1,000 and a little bit more than 1,000. We know that those publications may refer to the same records, but it's roughly like our list today, 4 years later, it's roughly that, like 1,200 speleothem records globally. And what we achieved, and I'm just going to step forward a few years, what we achieved is a database that has 700 records, so more than half of what's available in there. It's within that database, which is far more than what we thought we would achieve at that time. So why are speleothems important? And you may know already, well, compared to other paleoclimate archives, there are some hydroclimatic limits on the growth of speleothems, but their distribution is basically constrained by the suitable carbonate formations. And this means that we can find them at very high latitudes or very tropical latitudes in a wide range of climatic conditions. So some can be found in Siberia, in extremely cold climates where you would not find Poland, for example, or to very arid regions such as Israel or Australia. So speleothems have that potential of providing information about past terrestrial climates in areas where other records cannot provide information. And as I said, the main objective or the primary motivation of that was that there were already some isotope-enabled climate models. Over the last several years, there's been more efforts put into reconstructing isotopes in precipitation. The first previous generation of models, most of them were not isotope-enabled, and as what you measure in the speleothem are isotopes, you really need to get the isotope-enabled model simulations. And there are several, like here you just have an example of the PIMID-3 run of models that do have those isotopic tracers. So we have both, and there was that potential of using the isotopes in speleothems as to evaluate those climate models. And some of you may know, oh, it's not the same. No, it's not. Like, the isotopes in precipitation are not exactly the same as the isotopes in the speleothems, but they are related. So the isotopes in the calcite, in the speleothem, are related to the isotopes in the deep waters, which is a combination of the isotopes in precipitation and in cave processes. And I'm putting that as a black box, because when you use the isotopes to evaluate climate models, and you see that later in the talk, you don't do exactly one-to-one. You look for directions, you look for trends, for magnitudes. So all that in cave processes that can affect the isotopes in precipitation can be put in that one box. And basically what I've been doing is looking for general trends. So if one record just deviates from that trend, it's fine. We're just looking for robust global or regional patterns. So we can put that in cave box, in a black box, sorry. So what I mean is that, and I'm not sure how many of you are very familiar with the speleothems, like, okay, oxygen isotopes in precipitation in the climate models, let's get that output, and let's get the output for the speleothem records and see how they compare. And then you'd think, well, the speleothem records, if they are representative or they are exactly the same as the precipitation, you would expect them to be very nicely matching each other if they are within the same cave or in the nearby caves. So you would expect different records to perfectly overlap as the ones you have on the screen. However, that is not always the case. And in most cases, it's not the case. So when you have a large compilation of records, you're able to extract the main patterns instead of relying in just one if you only have one record available for a given site. So in order to compare and extract these big patterns that I was interested in, you need a database. You need to standardize all the data and put it together. So there was an interest from the modeling community in using speleothems. Problem was that first they were using them at face value as a representative at 100% of that precipitation isotopes, isotopic composition. And there were a couple of databases already available at the NOAA repository. One of them in 2012, and it didn't have a lot of records. It had only 60 speleothem records, all of them taken from NOAA and put together in one file. And they had no dating information, and we know how good and important the dating information is. There was no standardization of the records, no quality control. They were just taken and put together into like one CSV file. Then there was another compilation published in 2016. It had 200 records, all of them as well available at NOAA, and it was focused on the paleoclimate period, like modeling periods, like the mid-Holocene, the LGM, the Lake. And this one was also created by climate modelers. If you know the speleothem community and you look at the list of authors, you would not recognize many. So basically, in that sense as well, there was just ages and isotopes for those periods. And they were being used at face value. So we thought we could do better. We could put together the speleothem community and put together all the data, all the metadata, and make some recommendations as to how to use that data and directly how not to use it at face value. So what we started like back in 2017, we did a brainstorming sessions to put together like a structure of that database as what would be the minimum that we need to have all that data in a sensible way. And we created this structure. This structure has a little bit buried since then. We've revised it because once you start putting into the data inside, you realize things that should have been different, but it's basically the same. So it's a relational database. We have the site, the information and the metadata from the site, from the entity in database language is the speleothem, basically, the record. Then we have the dating information. We have the chronology information, so the isotopes and the ages in which each sample corresponds to. We have the measurements. And in this case, we decided to go for the isotopes. And even though we were more interested in Ogden isotopes in terms of modeling evaluation, we included as well the carbon because that's useful for other scientific questions. So we decided to do this, and this isochronology that I have at the top right, this was added in a subsequent version of the database, in the version 2 that I'll talk to you like now in a second. So basically, we published that database, like the list of co-authors, including the CISL working group members here, it's around 150, and which was like a lot of people. I had the feeling as the coordinator of the whole group that the community received this initiative very well, and that could be done by the number of records that were submitted to the database in the first and then in the second version, and the number of authors of our database paper, which is quite high. And I don't know if any of you have coordinated a publication with this number of authors, but it's a mess. It's not easy. It's something that I've learned a lot over the last few years. So basically, this database, we designed it for the isotope modeling community to evaluate their model outputs and to explore regionals. So to go from like the one single record in one place to larger patterns, to larger signals. And on this regard, we had a special issue. CISL has like a pyramid structure with the regional coordinators that were the one doing the hard, like I was coordinating, but they were the ones doing the hard work in looking for the records, the data, and chasing the authors, because not all the data is publicly available. Like now there's more and more journals asking to put the data, the raw data on repositories, but all publications don't have that. So all these regional coordinators were doing a big effort on getting all that data, because the SciCell database only has raw data, like raw, and everything is with the aim of being replicable. So we have a lot of data, of metadata in there. And then these regional coordinators were put together in areas, so they all wrote a regional paper in this special issue to present what could be done with that first version of the database as a preliminary investigation of what was there and what could be achieved. And we learned a lot. Like there was, like we had the main, like the presenting paper in that special issue, and where we tried to put together what we had learned of that initial phase of SciCell. And basically we realized that uncertainties are the big forgotten. No, like 80% of the records had no uncertainties whatsoever, which 85, sorry, which reduces what you can do with them in today, where the computing skills are completely different than 20 years ago. So this is something that was constraining some of the things that some of the members wanted to do. Mineralogy, that's not something that is reported in most of the papers. So we had to chase one by one, and you'll see why later, one by one, the authors to let us know what was the mineralogy, was that analyzed or not. And then there's a lot of data that is usually missing when the records are made publicly available, which prevents other researchers to reproduce what was done originally, which it makes sense, assuming that the mentality of open data has changed over the last few years. And what we wanted to do is to highlight the importance of that. For example, BP. BP, not everybody understands the same if you don't specify what you mean. In most communities, BP 1950, before present, being present 1950. But in the speleothem community, in a lot of papers, BP does not refer to that, but the year in which the uranium thorium chemistry was done. That can be 50, 60, even 70 years of lag, which when you're just working on one record may not be important, but it is important when you're comparing records, when you're putting more than one record together. And this was also like a bit of a nightmare to get back as publications 20 years ago. What did you mean by BP? And that's something that we want to push. And I'm pretty sure that all the SciCell regional coordinators that will be reviewing papers in the future will make sure that all that is properly reported. But that's something that if we hadn't done this exercise, we probably would not have noticed. Then it came with the age models, which brought us to the next stage of SciCell. So having 300, 400, 500 records requires, so one of the things we are very happy about is that we did a very strict quality control on the data. We checked everything we could think of, everything. And one of the steps was visualizing the 8-step model of that record to see whether it made sense or not. And the axes are very tiny, and these records are anonymized, so that I don't want to point at anything or anyone. Just as I want to pass on the idea that these were some of the records that we could find. You have on the y-axis the depth, and on the x-axis the age. And that's fine. That would pass our quality control, but you could also say things like this. And that was quite common. Age inversions, as the ones you have in here. So certainly the trend is the opposite. It gets younger as it gets deeper, or weird form like shapes, or very abrupt changes in growth that are not consistent with anything, or data in between hiatuses that were not constrained at all by dates. So when we realized that this was the case in some of the records, surprisingly high percentage, in a way, we decided and we thought that we could redo, retest, and not saying something completely different to the original authors, but test what was going on here. Was it depending on the method that was being used to create the HDEM model? Was it because there was no critical assessment of those HDEM models? What was causing this? Could we test that? I think that we had a lot of data, so that was an opportunity to do something objective and something robust. So what we decided to do was to create that size-chronology, do an HDEM model intercomparison as well. So this at the top, that's at the percentages of dates in CISR version 2 and of H model types. And the ones that are highlighted in yellow are the ones that we reproduce. So we took all the uranium, thorium dates, like all the speleothems dated with uranium, thorium dates only. We didn't go for the more complicated HDEP chronologies with just like multiple methods, laminations, carbon-14. We ignored those because the larger fraction of records are uranium, thorium dated. And we redid the HDEP models with the most common methods: linear interpolation, linear regression, and then we used Stahlage, Copra, Oxcal, Bacon, Bikran, Stahlage, Copra, Oxcal, linear interpolation, linear regression. And that gave us an overview of the performance of each of the different HDEP models and the uncertainties. We could add then uncertainties on those HDEP models, apart from trying to fix those inversions that we found. So this was a way as well to QC, to quality control the database, because we realized things that were missing. And it's when you use the database that you realize of things that are not correct. And provided and create as well ensembles so that we could use those ensembles. As ensembles are iterations of the HDEP model. So it's keeping 1,000 relations of that same H model and in an iterative way. And that would allow us to better quantify those uncertainties. So this is an example of the performance of the different HDEP models. And there is now like an evaluation paper on the performance of its HDEP models on its way. It is taking some time. So here you have the uncertainty quantification and how each of the different HDEP model approaches perform with that. So you'll see, for example, here, like these are hiatuses, the lines. Here, there's no gap. That's Bikran. You cannot enter hiatuses in Bikran. It doesn't accept that entry. Or you have Bacon, which you have these reversals at hiatuses. Then in Stahlage, you have the same. You cannot enter the hiatuses in it. So Copra, it also has these reversals, that's the dark blue. And then you see that the linear regression and the linear interpolation have very, very tiny uncertainties. So each of the different HDEP models perform differently. And that's important because even though uncertainties have been ignored or not taken into account for a long time, the higher computation skills and computation power that we are having now today, like allows for some for incorporating these uncertainties onto our analysis. And this is just saying that depending on the approach that you use, you have completely different results. So we need to be very critical as to whether the uncertainties that we are reporting are the best approximation or not. So what we did later was to put together all the different HDEP models and QC them. So we did not accept all the models that were computed because some of them were crazy. So we automatized these 8 models, we run them all, and then we looked at them one by one. And we created like an automatic checklist, and we did like an expert evaluation of those 8 models, because some of them act or like perform in a way that is not physically plausible. So it's important to look at them and have that human eye investigate as to whether that makes sense or not. So we had 3 different checks to start with. One was if there were reversals in the chronologies, we completely rejected that 8 model. Then if the final chronology should be flexible, should follow flexibly the growth rate changes, so that most of the dates are within the final 8-step model, so that it's not abrupt, like it doesn't have abrupt changes in growth as the ones we had seen before. And then that the temporal uncertainties increase around the hiatuses before and after the hiatuses. That's important as well, because you cannot date the hiatus. So it has to, like the uncertainties have to increase when you get closer to that. So we ended up with more than 2,000 size and 8-step models for 503 records out of the 690 that we have in version 2, in CISA version 2. And you can see here that not all models perform the same way. So for some records, some approaches work, some others crash. So it's not easy to say this is the right approach. So our recommendation is not to use this model, the 8-step model, or this other, like this approach or this other approach. It's use more than one. Use more than one, test how the output looks like, and keep the one that seems more physically plausible to your data. And yeah, so it was challenging, and there's no way we could recommend a best model. So then, moving on to a different aspect of CISL, I said that the main motivation was to provide data to evaluating climate models. And we did a community protocol on how to use that data. So this paper, more than evaluating a climate model, was designed to talk to the paleoclimate modeling community and say, hey, here's our fantastic data set. I'm sure you want to use it. Let's use it right. And this is how we recommend that you should use it. And there's been several groups already using the CISL database for this purpose, following our guidelines. So it seems that the message has gone nicely. So this was published like summer 2019, and it was before we produced the CISL version 2. So it was using like a mid version, a version 1B, because after we created version 1, we realized that we were missing a lot of records from the mid-Holocene and the LGM that were the 2 periods that we were interested in to do this exercise. So in one of the workshops that we had, we put a lot of effort into increasing the number of records for those 2 periods so that this exercise would be nicer. So we use this version 1B with 456 records that you have at the top, and we use the ECAM5 model output. We used ECAM because I'm familiar with ECAM. I used it for my PhD, and I know Martin, and it was readily available to us. We could have used any other paleoclimate isotope-enabled model. So we focused on mid-Holocene and last glacial maximum because those are the 2 entry cards for PIMIP. And I don't know whether you're familiar with what PIMIP is the Paleoclimate Intermodel Comparison Project. And basically it brings together all the climate modeling groups that do paleo. So basically, they have to simulate either the mid-Holocene or the LGM. So these two time periods are the ones that are there for most of the isotope-enabled models in PMIP. So we use this partly because the experiments are the entry cards for the PMIP4 simulations, and partly because these are the PMIP periods where we have the best coverage of speleothem records. And I think, well, LGM, best coverage, better than the leak. So those were the two time periods that we could use, removing the past 1,000 years. We wanted time slices. So the first thing that we had to do was screen the records. When you have a database, that's relatively easy. You can just say, give me the records that cover this period. We used 6,000 years ago. Well, climate models are like a snapshot, like a photograph of that period. We use 6,000 years plus minus 500, so that we would have a window. And with the LGM the same, 21,000 plus minus 1,000. So ideally, we would have used the temporal uncertainties. We couldn't, because at that time there was almost no temporal uncertainties in the database, but that would have been the ideal. Then we had to treat that data. And that's where the mineralogy came into play. And we realized that we were missing that. And you have to think that when you have a database, if one of the parameters is unknown, that records automatically gets rejected because you cannot do that same treatment compared to the others. So you want to have variables that are as complete as possible, that you have all that information for as many records as possible. So basically in here, I'm pretty sure most of you or some of you already know, like, because the isotopic fractionation between the water and the carbonate, it's different between calcite and aragonite. We had to select and treat different the records depending on their mineralogy. And similarly, we had to remove the record, ignore or omit like the records that had mixed mineralogies that were not either one or the other, or the ones that we had no idea what mineralogy had. All this information is was given to us by the original authors. We never assumed what it was. Like, we read to original authors all the time for everything, every variable. So then we have the temperature-dependent fractionation factor that we had different equations depending on aragonite and calcite. Problem was the temperature. You don't have temperature, but you need to do that conversion. Otherwise, you're comparing with the models and you're comparing oranges and apples. Like, you need to put everything in the same unit, the same scale. So that's one of the limitations. The K-var temperature is unknown, so we had to use simulated model data for that, which is not ideal, but that's everything we can do. Like, there's no other options. And using the correct fractionation equation using the mineralogy, it's very important, particularly in the LGM, as the offset is larger and at lower temperatures, as you can see in this figure. So once we had converted all the speleothem records onto their drip water equivalent, we could then test as to whether they were globally able to reproduce what the simulations and what the observations were doing, So we first started with the modern. And it's important to start with the modern because that's where we have more data. And then we can say, well, if it reproduces the modern, we can assume that it does not do a very bad job in the past. So what we used here is the OIPC data. That's a data set of interpolated weighted delta in precipitation, that it has all kind of data put together, and it's gridded and interpolated, and it's very good when you're trying to look at global patterns. It's very useful. So we put our records, modern records, that's for the period where the GNIP data is available, 1960 to 2017. So we did those averages as well on the isotope sisal data, and we compare it. And as you can see here in the scatter plot, it's not bad. You have some departures. That's fine. We are not looking at why one single record deviates from the line, because we are interested in the general plot. So as you can see, there's no systematic bias according to latitudes. Latitudes are the, oh, I forgot the color bar. Latitudes are the colors. So there's no systematic bias according to the latitudes. The correlation is high, and the trend is like more or less on a one-to-one line. So while the discrepancies of each of these individual dots can be due to cave-specific factors, such as like seasonality of recharge or non-equilibrium fractionation processes, or soil atmosphere interactions that affect evapotranspiration, or the uncertainties in the fractionation factors that we've used to convert the data before, or many other processes, we can see that more or less it matches, and this is like a good match for what we're looking for. So then we looked at it temporally, and temporally that is exactly what we expected as well. So here we have the observations from the GNIP, the Global Network of Isotopes and Precipitation, and that's the interannual variability, global. Everything is like global here. Then you have the same from the model, the ECOM, for the same years and sites. And then we have sisal. So when we did these are not comparing the same sites and the same years, because those data sets are not all complete geographically and temporally. So what we did, we extracted ECOM in the same place as the sisal records for the same years that the isotopes were reported. And that's this one here. And we can see that there's a big change. So there is a larger interannual variability in the simulated isotopes and precipitation compared to sisal records, speleothem records. And that makes sense. That's basically showing you the degree of smoothing that you have in the speleothem records over time. So we smoothed the ECOM to see globally what was that range. And it starts matching at five years. So that's basically reflecting that low-pass filter of the karst processes. So then I said that the models were like snapshots, and basically they are presented as anomalies with respect to a modern problem. Speleothems don't grow continuously, mostly. This is one of the figures where you see the speleothem records and for what years we have samples, and it's quite patchy. So it's not easy to create anomalies from speleothem records. So we had to select a modern period that was as big as possible, thinking that you would not increase a lot of uncertainties, but you'd get you would maximize the number of records for which you could calculate anomalies. So we played with that. We selected a relatively big period to do those anomalies. And we produced the anomalies. And here it's what we are comparing. And so you have mid-Holocene minus the pre-industrial. That's the anomalies for the mid-Holocene. Mid-Holocene. The map is the model. The dots are sisal, of course. The lines are non-significant changes. And here is the same for the LTM. And you'll say, well, you had 400 records. What's going on here? You have less than 10 for the LTM. Well, having to do the anomalies reduces dramatically the number of records that we have available. However, like with the data that we had, and now it would be better with version 2, but at that time with version 1b, most of the records show a change on the same direction. So it's the model blue and the sisal data blue or red. So yeah, the same direction, that's fine, but we cannot extract a lot of things because the amount of data, it's not very large. However, it was promising that at least the magnitudes and the directions were not that different. We did as well like LGM minus mid-Holocene to see whether we were increasing the number of records available, because then you don't need to have like a modern sample, and you do increase some the geographical coverage, but still you cannot get regional patterns when you have like 1-2 records for an entire continent. So we had to think about something different, and this is where we did something new. Basically, we were, okay, we cannot do the classic anomaly approach. Let's look at trends. Let's look at trends, geographical trends, within the model and in the isotope, like database, in the CISL, see whether we can extract something. And that's what we did. So we extracted trends for different periods, the same trends. You have a different coverage of records on each of the periods. And we look at how that changes. So what we can see in here, for example, is that in the model data, we have a change in the transect. So this is isotopes on the x-axis and latitude, and that's the section that it's going through, from the north to the south. So you can see that there is this fundamental change in that transect. But here it's with the uncertainties, of course, trend, we can't say much. We cannot say that it differs a lot. It's fine, it's acceptable, it is the same. But here you really see that something's going on. Something is going on in the mid-Holocene in how the model is performing. And we do know that this model in particular, the ECOM5, has problems in simulating the hydrological cycle in the mid-Holocene. So this is in a way what we were expecting. So we can maximize and we can use more records than the ones that we could use with using the anomalies, and we can still identify some problems. We can also use this in conjunction with other data sources. In here we have it with pollen data, with climate reconstructions using pollen data. And these are LGM transects. And you can see that in a way, our scarce number of records follow what we've simulated. So we can in a way use that data to identify these first order trends. So with this, we established this protocol. I'm not like this is just like a summary and some other things that I haven't mentioned, which is being used, and we think that it will increase the visibility of the speleothem records outside of the speleothem community. But now, like phase 1 of CISL came to an end, and I'm going to finish now in a couple of minutes. See the time. So it finished last year, and we achieved a lot in those 3 years. We did a special issue with these regional papers. We had these 3 database versions with their papers, this protocol to increase visibility of speleothem research outside of the community. We presented CISL a lot in many conferences. We have received interest from over 300 people interested in either contributing with data or using the database. And we've achieved more than half of the records that we know exist, considering that some of them are very old papers, that it's very difficult to get hold of the data. And we are now receiving like publications, like recent publications that want to get data onto CISL. We have a lot of 2018, 2019 published records in CISL, or with the people really willing to contribute to that open science and big data compilations. And we did this exercise with the HDEP models that was quite insightful. And I hope we'll have that paper out soon if you're interested in that intermodal comparison. So now Sisal is moving on to a phase 2 with a completely new committee, steering committee. I've stepped down as coordinator of Sisal. I think it's time for me to move on from that little kid that Sisal has been in my research life and let other people bring new ideas and new things onto it. And their objectives have changed now. So what we're going to do is a step forward and bring together cave monitoring data, trace element data, everything thinking about how to increase the way, improve the way in which we are interpreting those isotope records, which are not straightforward. And it's always important to have other sources of data supporting the interpretations. So that's it for me, but I have to acknowledge and give credit to everyone who's contributed to this big and huge community effort, which I hope will continue. And I'm sure I've forgotten a lot of people here, but thank you all. And if you have any questions, I'm here to answer them.
Right, thank you so much, Laia. Questions, guys?
I'll start sharing so we can see.
Yeah, so we can, all right.
Uri, if I can start, is that okay?
Yes, go ahead, Yoni.
So, Laia, thank you very much. This is amazing. There's no question. This is such a huge source of knowledge that you're putting together. It's unbelievable. So I have sort of a big picture question, and that is, now that you have all the data, which model should we believe? What is the isotope enabled model that actually gets the East Asian monsoon properly, gets the African monsoon right, gets LGM dynamics proper?
Short answer, none. So it depends exactly on what you are. Okay, so my experience is that you can't take the models as they are for granted. You can use them to understand the physical mechanisms that would lead you to that value or to that pattern, but not to do like a one-to-one comparison in a way. So there are several methods that you can use paleoclimate models, and then you would need to discard them if they don't match the observations at all, because then that means that something in the physics of that model is wrong. So I haven't introduced what I've been doing over the last few months, but I'm working on benchmarking the last generation of models with pollen data. And God, the results are not great, are not coherent across models, but that doesn't mean that you cannot use them. You can use them in a way that help you explain the mechanisms behind your data. And that's why you usually need several simulations with different settings to see which one in that case would perform better. And in the tropics and in the monsoon regions, when it comes to advective precipitation, it's limited. The performance of the models isn't great. There's been some improvement in between PMIP3 and PMIP4 models, but still there's a lot to go. So I would use them with caution, and I'm using models for the last 10 years, and I think they are extremely useful, but they need to be used not at face value, the same way as I said, paleoclimate modelers were using speleothems as face value, and that's wrong. We cannot use models at face value either. I don't know whether it answers. I can't say that model works great.
No, but I think maybe it's time to flip the power dynamics, right? Where as paleo people, we've always looked at modelers and said, "You are our gods. Tell us what we're doing wrong," right? And now you have this huge database, and maybe it's time to say, "Look, this is the data. This is where these models are getting the parameters wrong." And do something about it.
the funny thing is that it works the other two ways. So from data generators, like, oh, you're my God, you're doing that. And then it's the other way around as well. When you start talking with polyclimate modelers, they're like, oh, give me data because you are the reality. So it's that paradigm that both are like stuck in the other one does better. And I think it's time to just, put the two communities together. And CISR has done a great job, I think, in putting together, like the last workshop that we had back in 2020 in Xi'an in China, half of the attendees were climate modelers and half were speleothem people, let's say. And I think that's the way to go, because then we will speak like a common language. It's like the annual resolution of the speleothem records. That's something that speleothem people know. It's not real annual most of the time, but a climate modeler, if they read annual resolution, that is annual resolution. That is annual, like really representing that year, that given year. So I think that there's a need to talk more between communities and to reduce this gap in vocabulary and in how the data and the models perform. I think that's very important.
Cool. More questions? Anyone else? Okay, I have a question. So when you look at the, you compare the modern precipitation with the prediction from your speleothems, you have to give some temperature. So you just assume modern day temperature, season, how does it work?
In that comparison, I use the CRU temperature, which is a global database based on observations. So I use that as the mean annual temperature as the cave temperature.
And a follow-up, when you compare, the model predictions with your data, do you also use the output temperature, I guess, to predict?
In the modern, I use the observation-based temperature because it's better than the simulated temperature. In the past, I had to use the simulated temperature. Yeah, for mid-Holocene and LGM, I had to use the output from the model.
Got it.
That's what we can do. We can't do better. There's no other source of temperature. I was trying to use, like, one of the tests that we did at that point was using the temperature reconstructed from Poland, the gridded temperature from Bartline. I don't know if you're familiar. Bartline around 2011. It's a gridded climate reconstruction. So it's a reconstructed climate in a gridded data set based on Poland, and it has temperature. So I use that temperature, but then it's in some areas there was no reconstruction because it's constrained to the area where you have Poland data. So it's not covering the whole globe. So I was reducing even further the number of records that I could use because that temperature, reconstructed temperature, wasn't everywhere. So I decided at the end, like, the best we could do was to use that simulated temperature. I have to say that model data, like simulated temperature, is the best variable. The problems come when you go into the hydrological cycle, precipitation, and any variable, moisture, any variable related to the hydrological cycle. But temperatures are quite similar across models and quite good. So you are, of course, adding uncertainties, but yeah, that's the best you can do right now.
I see Yuval has a question.
Yeah, I have a question. So it's more of a, so I have a question that's kind of a leading question to you. What do you need? Because often in these seminars, there are people who are doing this work with this unknown proxy or looking at this lake or this tree somewhere, and they when you say what you need, they're like a bulb lights up, and then they're like, we can do that together. So in order to improve research such as the one you've shown us, what do we need?
What do we need? We need data. So we need people to be involved in opening and making their raw data available, not just in the speleothem community, but in all data generators community. And well, for us in particular, speleothems. So we would need my wish would be, if you know people who have produced data that is somewhere in a computer but not available online, ask them to make it available. Ask them to share that data, because it's just one record maybe, but one and one makes a big difference. And we can see the potential between version 1 and version 2, which has increased a lot. Like if I repeat the study that I did for that big picture paper 3 years ago, now with version 2, we would get a lot more data. And I quickly did that at some point, and it was like 3 times the number of data that we had. And then you can tell more things and you can advance, and you're not constrained on those comparisons with like 10 data points. Like thinking on a database mindset, the more data, the more robust the patterns that you're extracting are. So that's what I'd say. Data. We need data. And it's not about that we needed to make it ours, to make sure that the patterns that we are extracting are robust. And ideas. If you have ideas as to what to use the database, get in touch with Sisal, because we are kind of brainstorming of new ideas and ways to move this forward. So we have these two aspects, like the data part and let's use this for science. So if you're interested in using Sisal for anything, get in touch.
I think ideas.
We have a lot of people.
Yeah, I think ideas is a good thing. Like you could contact a lot of people will think, oh, this is this group and it's working and it has their own people, but it's not true. You can email Sisal, say, I have a paper that I wanna lead, and they will give you the data, they will give you the tools. Some people from the work group will join you, and whatever you don't know how to do, they will probably, some people will know how to do, and then you just need to lead the paper.
Yeah, that's a good thing of a big community. There's always someone who knows. Yeah, Mira, I think wanted to ask
It's not
something.
a closed group. Definitely not a closed work.
We have another question from Mira.
Hi, Mira. Good to see you.
Oh, Mira,
You're
you have to
muted.
unmute yourself.
When you show the models, you reduce the number of places where you can use the speleothem to make the model better. So maybe you can tell us why there are regions that you get better data and why there are regions that you get less better data, although there are quite a lot of data from there.
Sorry, I'm not sure I got it all. Can you say it again, please? Yeah.
When you show the map with all how you reduce the number of region or records that you are able to use the model, why there are regions that are more usable record and regions with less usable records, although there are quite a lot of records from this area.
Yeah, so that's the problem when, like, I understand is when I had to create those anomalies.
Yeah.
So the problem with the anomalies, okay, models are always expressed as anomalies. That's the first thing. And the way they do that is to be able to compare different models without like removing the bias that you'd have in absolute values. So to compare the speleothems to the model, you have to to convert them to anomalies as well. And those anomalies are with respect to present day. Some models use pre-industrial, that would be 1850. Some others use modern data, like the second half of the 20th century. So most of the speleothem records don't grow from the LGM to present. So you would have data from the LGM, but that same record does not cover the present day. So if it doesn't cover the present day, you cannot convert that to anomalies because you don't have a modern to extract that from that LGM data. So the areas where you have more data points in those maps for the LGM are those records that do cover the whole of the last 22,000 years, which is not common. And most of speleothems don't cover all that period. So it's in some cases, it's because the publications are focusing on one period and they don't publish the whole record. In some others, it's because just the start record has only grown over that short period of time. One of the things that I tried as well to maximize the number of records was to use that global GNIP map that I showed you, like that modern isotopes in precipitation map to calculate the anomalies. But when I was comparing the anomalies from records that were that long to the same anomaly, instead of using the modern from the speleothem, using the modern from the data set, were completely different. Because you are like increasing the uncertainties in those conversions. So that lack of records growing for the last 20,000 years was the motivation to look for an alternative way to use those models, because otherwise it's ridiculous, because you get with 7, 8 records for the LGM that have grown like 20, all the way from then to the modern.
Phase 2, that's looking at the modern monitoring projects, water and calcite and everything, will probably help us produce more of the modern, benchmark data points. Hopefully.
We can't hear you if you're talking.
Yeah, good point. I was asking if there's one last question. Anyone? I see Yoni wants to ask one last question. Oh, and Amos.
Yeah.
I wonder if you used the data to reconstruct the last interglacial because of its importance for the future predictions.
Problem is that there's no global data for that was grown all the way through the last interglacial. We have now, my PhD student has now a paper in Reviewing Climate of the Past in monsoon regions using lake data and lake model evaluation, climate model outputs, but the number of records is too low. So that's why we didn't focus on the lake. It would be great to have as many records as we have for the mid-Holocene, but unfortunately, we don't.
And another, I wonder if you used fluid inclusions for reconstructing temperature within the cave itself?
No, we didn't. And there's a lot of variables that could be included in the database. The problem is that from a database mindset, you need that most of the records you need the records to have that data. You don't want a variable that is almost empty and that only has data points very scattered, because then you cannot use that information. And if we were using fluid inclusion data for the temperature, we would have how many records? Very, very few, because we need to be treating all records in a consistent way. So if there was a lot of fluid inclusion temperature reconstructions, that would be fantastic. And I wish there will be I don't know, in 10 years, but at the moment, from a database point of view, that's not feasible, unfortunately.
Thank you.
Okay. I think that we're going to finish here. If you have
Thank you for inviting me. It's been a pleasure.
Right.
Thanks.
Bye, guys.
Bye.
Ciao.
And of course, I'm at my email for any question. Bye.
Thanks. Bye.